Hello, everybody. Welcome to Mrs. Baker's Chemistry Corner. This is question 15 from Module 10, the metals module. Let's dive in. So, question 15, sodium is a reactive metal. Suggest why sodium is stored under oil. We store it under oil because the oil stops any water from coming into contact with the metal. Remember, all group 1s are stored under oil for that reason. Sodium burns in air to form sodium oxide, or Na2O. State the term given to a reaction in which a substance burns. So if we're burning anything, we've got a combustion reaction. State the color of the flame seen when sodium burns. Well, sodium burns with an orange flame. So write the chemical equation for the reaction that takes place when sodium burns in air to form sodium oxide. Well, we know that sodium as a metal is Na. We know that oxygen is O2 because have no fear of ice cold beer. That's our diatomic molecules that we need to remember. That's going to make sodium oxide. It's told us here it's going to make sodium oxide, and it's been kind enough up here to give us the formula for it. So Na2O. So now all we need to do is balance it. So we've got two sodiums here. So we need two sodiums there. We've got two oxygens here. So we need two oxygens here. And that's great. But our sodium's now out of whack again. So actually we need four sodiums here. Now it's balanced. So complete the dot and cross diagram to show the electron arrangement and charges of the ions in sodium oxide. So let's start with the charges. Sodium is in group 1, so they're both going to form a +1 ion. They're going to give one electron away. And the oxide is formed from oxygen, which is in group 6, so that is going to be a -2 ion because it's going to gain an extra 2 electrons. So now let's have a look at the electronic configuration. Well, if we look at the periodic table, then sodium is in period 3. Now all metals fall back and give away their outer shell electrons in order to achieve the same electronic structure as the noble gas that is in the period before it. So the noble gas from period 2 is actually neon, and it has an electronic configuration of 2,8. And so our sodium is going to end up with an electronic configuration of 2,8 as well. So all of those electrons actually belong to the sodium atom, the sodium ion. So we're going to show them using crosses because Cambridge had chosen crosses for sodium already. Now, for the non-metals, they jump forward to being the same electronic configuration as the noble gas in the same period as them because they gain electrons. So oxygen is in period 2, so it is also going to achieve the same electronic structure as neon. So it's only going to have two full shells. But we know that it had 6 of its own. So 1, 2, 3, 4, 5, 6. We show that these 6 belonged to the oxide ion originally by drawing them with dots. And then we're going to show that it got 2 more that it received from these 2 sodium ions when it gave its extra one away. And we're going to show those with dots so that we're showing they come from the sodium over. Sodium reacts vigorously with water to form aqueous sodium hydroxide, or NaOH, which is a strong base. Explain in terms of proton transfer what is meant by a base. Well, I've not taught you that yet, so I'd already put that in for you, that all bases are proton acceptors. We'll learn a little bit more about that in the acids and bases module. State a pH number that indicates the presence of a strong alkali. Well, we've been doing this since key stage 3. So strong alkali would be anything pH 11 over. And so let's go for pH 13. State the color of methyl orange in aqueous sodium hydroxide. Again, we haven't done that yet, but methyl orange is yellow when it's basic and it's red when it's acidic. The equation for the reaction is shown. So here we've got sodium metal reacting with water to make sodium hydroxide and hydrogen gas. It's asking to calculate the concentration of the sodium hydroxide in grams per decimeters cubed when 0.345 grams of sodium is added to 50 centimeters cubed of distilled water. It's telling us to assume there is no change in volume. Use the following steps. So we can just go through and just calculate the steps that we need, but I find personally Mrs. Baker's table method, trusty table method, works. So in this case, it's saying calculate the concentration of NaOH. So in this case, we definitely need 2 NaOH in our table method. We also need the sodium. So we've got 2 Na. It's told us that we've got 50 centimeters cubed of distilled water, but that's just to give us our volume for our sodium. So it's saying that we've got the sodium there in the distilled water here. So it's saying total the concentration is only 50 centimeters cubed. So we don't need to add the water in there because we're only using it for a volume. So we've got mass, mole, mR, and we've also got our moles, conc, vol triangle. So we're going to need to draw out our table method, and we'll put in everything that we know. Well, we know we've got 50 centimeters cubed overall. So we've got 50 divided by 1,000 gives us 0.05. So we can safely assume that we've got 0.05 as a volume here. The mass of sodium it has given us is 0.345. So we're going to put that in, 0.345. We can work out the MR of sodium, which is 23 from the periodic table. We can also work out the MR of sodium hydroxide, which would be 40. No, it wouldn't. It would be 23 plus 16 for the oxygen and 1 for the hydrogen, which would equal 40. And then it's also told us that we need to work out the concentration here. So we've got 2 already in our sodium column. So using our magic triangle of mass, mole, mR, we're also going to need our mole, conc, and vol. So mass divided by mR will give us our moles. So let's go to our calculator. Our mass is 0.345, and we're going to divide by our mR, which is 23. That's going to give us 0.015 moles. And if we've got 2 moles over here and 2 moles over there, then we've got a 1-to-1 ratio. So if we've got 0.015 here, we've also got 0.015 here also. Now we can work out the concentration quite easily in moles per decimeters cubed, because we can just use the mole conc vol, because we've got the moles and we've got the volume. So moles divided by volume, so 0.015 divided by 0.05 gives us 0.015 divided by 0.05 gives us 0.3. So our concentration in moles per decimeters cubed is 0.3. Let's go and fill in some of the things that we need to fill in first. Well, the number of moles of sodium added was 0.015. We're just now reading off our table. The number of moles of sodium hydroxide formed is also 0.015. The concentration in moles per decimeters cubed is 0.3 moles per decimeters cubed. And we don't need to worry about writing our amounts in here, because we've already got our sums written out in full over here. Now it's saying determine the MR of the sodium hydroxide and calculate the concentration of sodium hydroxide in grams per decimeters cubed. So we've already worked out our MR. We're way ahead of the curve here. So now we can work out how many grams we have in a volume of 0.05 by doing the moles times the MR. So in this case, we've got the moles, 0.015, If we times it by 40, which is the MR, it gives us 0.6 grams. Now that would be great. We've got 0.6 grams in 50 centimeters cubed. But 50 centimeters cubed is not a decimeters cubed. So we've got to go from 50 centimeters cubed up to 1,000 decimeters cubed. So in order to get from 50 to 1,000, I need to times by 20. I can work that out by saying 1,000 divided by 50 gives me 20. And then I can test it the other way by saying 50 times by 20 gives me 1,000. So if I have to times the volume by 20 to get it into a decimeters cubed, I also must times the mass by 20 to get that into the same magnitude. So to go from 0.6, I times by 20. What does that give me? That gives me 12 grams. So if I've got 0.6 grams in 50 centimeters cubed, I've got 12 grams in 1,000 centimeters cubed. So my answer over here must be I've got 12 grams in 1 decimeters cubed, or 1,000 centimeters cubed. So when sodium hydroxide is added to aqueous iron 3 chloride, the solid product is formed. So what's going to happen here is a double displacement reaction. So you're going to form sodium chloride and iron hydroxide. Well, we know that all hydroxides are insoluble, number one, but we also know that sodium chloride is definitely soluble. Sodium chloride is salt, and if we put some salt from our cupboard into water, then it's definitely soluble. So the solid product that they're talking about must be the iron hydroxide. So if we jump down to name this solid product, we know that it's iron 3 hydroxide. That's just by process of elimination. And name the type of reaction when a solid is formed from two solutions. Well, the iron 3 hydroxide is a precipitate, so it's a precipitation reaction. And state the color of the solid product. Well, we've got iron 3 here. And so iron 3 is always a brown color. That's how we know that we've got iron 3, because we get that nice brown rusty color. Write the ionic equation for the reaction and include state symbols. Well, whenever you have a precipitation reaction and it tells you to write the ionic equation, it is really, really easy, but you always start at the end of the equation, only for precipitation reactions. So the precipitate we've already said is iron 3 hydroxide. So that must mean it's Fe and then OH3. And we know that that must be a solid because the question has told us it's a solid. Then we're going to draw our arrow and we're going to just write the ions that make it up. So we've got Fe3 plus added to OH minus. And what we need to do is now balance it out. So we need to put a 3 in here. And we've only got one ion, so that's not a problem. But then we mustn't forget our state symbols. If it says include state symbols, then it is definitely giving you a mark for including state symbols. So that would be your ionic equation for this reaction.